Okay. So how are we doing on sharing the screen?
Not seeing anything quite yet.
Oh, if I click on share, would that help?
I see it.
All righty. So, so I'm gonna try doing the whole slideshow thing. Does that work? Oh, look at that. Okay. So, in my little PR piece for this, I said that it was a 3 million year saga. Actually, it's more like a 14.5 million year saga to look at sort of the entirety of Hell's Canyon. And I also wanted to make sure that I acknowledge the people whose research I'm actually just sort of talking about here today. And those include Matthew Morris, who just finished his doctorate at the University of Oregon. And basically his work has been looking at the incision, the major incision of Hell's Canyon over the last 3 ± million years. Jim O'Connor, as you know, has worked on the Bonneville flood and the Ice Age floods in the Columbia Basin. You're going to be hearing from him. And so my part about the Bonneville flood is really short, and I'm sure that Jim's information is going to be way more detailed and actually more up to date than what I have. Tracy Vallier continues. He's now in his 80s, and he's still spending his summers in Hell's Canyon mapping the geology and also looking at the formation of the canyon itself. John Elliott Allen and a number of other geologists have pieced this story together. I'm merely the person who's going to be trying to take their work and put it all together in a semi-coherent saga this evening. Okay, so the deepest gorge in North America is, the photos are all mine, or virtually all mine. Hell's Canyon is the deepest gorge in North America, about 6,200 feet from the top of He Devil Mountain in Idaho to the river below. At the deepest part of the canyon, this kind of like measuring the Grand Canyon at its deepest point and saying, well, it's a little more than a mile in depth, but we have a bit more depth than even the Grand Canyon does. And so it has a long history of incising it, and there have been a number of attempts to date the formation of Hell's Canyon just as the Grand Canyon. That have ranged from, it was cut in about 7 million years to 2 to 3 million years. And I think that Matthew Morris's work has pretty much defined the age of the canyon itself. And so we're going to start taking a look at that. For anyone who doesn't know sort of where Hell's Canyon is, it's between Lewiston and Boise, basically, on the Snake River. Just a little bit of its topography. You'll notice that it has a deep point right in here. We're going to take a look at a couple of odd features of Hell's Canyon that have helped tell the story of how this canyon was made. Okay, so I already said that. So just to go over the geology really quickly, there are 2 geologic packages that compose the geology through which Hell's Canyon is cut. There are the accreted terrains, old rocks formed as islands and seafloor off of Idaho, 300 to 140 million years ago. And then above that, overlying it, unconformably, are the Columbia River basalts, which are in that area about 16.7, the Imnaha River, or the Imnaha basalts, to 14 million years ago, that get up into the Wanapum basalts. If we look at that on a geologic timescale, this is sort of what it looks like. We have this package of accreted rocks, accreted terrains, Permian, from very, very early Permian in the deepest part in Cougar Creek to Jurassic rocks in the area of Coon Hollow and this north central part of the canyon. And then most of the canyon is cut through the old rocks of the Triassic accreted terrains and then the Columbia River basalts overlying them. And what's really interesting in this area, so here's the early Permian bimodal basalts of the Cougar Creek complex near Kirkwood Ranch. These rocks in the Cougar Creek complex are dated at 296.7 million years. So they're not quite Pennsylvanian, but they're almost there. Much of the bulk of the canyon is Triassic greenstones and also sediments that were deposited around the periphery of the islands that the greenstones represent. They represent actually islands that were similar to the Aleutians or the Marianas in the composition of the lavas. And there are two generations. There's one Permian generation that are more silica rich, more silicic, and then there's the Triassic that are more basaltic. Overlying those, there's Columbia River basalts, which I'm betting are really, really familiar to all of you. Anyone out there never seen the basalts? That's what I thought. But what's really interesting in Hells Canyon and much of Wallowa County and some parts of Eastern Oregon is that here we have Triassic greenstones, 230 to 235 million years, and immediately above them, with no break whatsoever, in most places, are the Imnaha basalts. So we go from 235 million to 16.7 million with nothing in between. Now, in a few places in the Wallowas, although not in Hells Canyon that I know of, there are gravels that are Eocene in age, and they're surmised to be Eocene because they contain Challis volcanic clasts. So the Challis volcanics were erupted in Idaho. They're between about 50 and 40 million years, similar to the Clarno Formation in Eastern Oregon. But there's none of that age rocks in Wallowa County. But during the Eocene, there must have been ancestral rivers that were running from what were high mountains and now exist as western Idaho ranges that shed their debris across Eastern Oregon in what were probably like huge alluvial fans, because these boulders are 2 feet, sometimes 3 feet in diameter. They're quartzites. So that's kind of the scenario of what the geology here is like. And I'm going to just briefly talk about three different episodes in the incision of Hells Canyon. Uplift after most of the CRBs were erupted, and delamination, which was the sort of the engine of uplift of the Wallowas. Stream capture and drainage of what's known as Lake Idaho, and the Bonneville flood, which came out of Lake Bonneville. So we will take a look at each of these as we're going on here. So this is just kind of a regional map to show where the Snake River runs these days. So it starts up here in Yellowstone and makes its way into Idaho, swings around through the Snake River Plain, cuts its way up through the boundary of Oregon and Idaho. The Salmon River and the Clearwater Rivers are now tributaries to the Snake, and the snake finally ends up pouring into the Columbia, not far from where a bunch of you are watching this evening. So that's the Snake River that we know and love. But the Snake River, like all of us, has gone through, I have no idea. Okay, so here we go. Snake River, Columbia River, Salmon River, Clearwater River. Okay. So the Snake River has gone through a number of changes in its history. And we're going to take a look, first of all, at uplift and delamination, 14.5 million years ago to 3.5 million years. So what happened as the eruptions of the Columbia River basalts began to wane, if you imagine that beneath Northeast Oregon and westernmost Idaho and southernmost Washington, there was a lot of basaltic lava and magma chambers. And particularly beneath the Wallowas, which seem to have been the epicenter of a lot of eruptions through the Chief Joseph dike swarm, there was the deep crustal root of the Wallowas was essentially not really melted away, but it was heated to the point where it began to peel away from the upper crust. And that was a little bit like taking the iron or the ballast out of a ship and allowed the Wallowas to begin to rise and uplift. And so this started at about, we think, 14.5 to 14 million years ago. And it's continues probably, at least the trying to compensate for this loss of mass continues through today, because we still have earthquakes on the Wallowa Fault, which basically runs up through the base of what we call Alder Slope. This is Wallowa Lake. Here are the Wallowa Lake moraines, the East Moraine, the Terminal Moraine, the West Moraine. So this is taken from Mount Howard. And Wallowa Fault runs through here. It's not a single fault. It's there's a series of multiple faults, but it's probably originally may have been a thrust fault that was then reactivated as a normal fault. There are also equivalent faults on the south side, the Pine Creek Fault and other Eagle Fault on the west side of the Wallowas as well, that allowed this uplift. The Sierra Nevada went through this, is a range because it went through the same process. So did many of the Klamath ranges. So delamination is a process that's been sort of documented in probably the last 20 years or so. And it's the reason that we have the Wallowa Mountains. Okay. So the last slide mentioned that there was about 7,600 feet of uplift. This is the top of Chief Joseph Mountain. And you can see this brown stuff. It looks kind of like chocolate icing on the top of the mountain, or maybe like a really giant Columbian mammoth took a huge dump up here. But whatever it reminds you of, what it is Columbia River basalt, specifically Imnaha basalt. And we can match this basalt flow to a basalt flow at the base of the Imnaha sequence at about an elevation of 1,200 to 1,300 feet. So this is around 9,120 feet. So there's a real easy way to determine how much uplift there's been on this fault. So what does that have to do with Hell's Canyon? So on the south side of the Wallowas, we have the cornucopia. This is a Google Earth shot. On the south side of the Wallowa Mountains, we have cornucopia, the cornucopia stock, the only truly rich gold-bearing place in the Wallowas. And coming off of cornucopia, it's granitic rocks, and it's overlain by some Columbia River basalts, and has Columbia River basalt dikes running through it. And then coming off of cornucopia, there's this little stream called Pine Creek, which I've outlined in red. And it goes all the way down here to Copperfield and what's called Oxbow, where there's a strange bend in what's otherwise a completely straight, or nearly completely straight, canyon of the Snake River. So as uplift began in the Wallowas, it provided a much steeper gradient for Pine Creek. And Pine Creek, according to Matthew Morris's work, had cut a canyon that is now known as Hell's Canyon, or the Snake River Canyon. It was about 1 kilometer deep over the course of 4.5 to about 3 million years. So there was this nice pre-existing canyon, at least partway in this direction. And on the other side of the river, there's also a stream called Indian Creek, which has its headwaters right now up here, and was also undergoing a smaller but a significant amount of delamination and uplift as the crust began to peel away from the granitic rocks in the Seven Devils and in the Idaho batholith. So this stream as well was able to cut a canyon, but not as deep a canyon as Pine Creek did. So we have a pre-existing canyon. And Indian Creek, as we're going to see, used to run, you can kind of see this canyon coming down here, and going this way. So let's take a look at what the ancestral Snake River might have looked like. The ancestral snake, up until about 3 million years ago, as far as we know, ran basically, where did my little cursor thing go? Here we go. Ran basically from somewhere in the east across what's now the Snake River Plain. And then there's a lot of controversy over where it went from there. It might, some people think, have curved and gone into Nevada, or have curved and been sort of the ancestral Klamath River running out here or running out here. Later on, by probably 5 million years ago, it may have been draining basically either in this direction, and this is also a proposed 12 million year old channel coming this way. By 5 million years ago, it may have been running through the Grand Ronde Valley and coming into what was then the Clearwater River, or the Salmon Clearwater River, somewhere around the Umatilla Basin or the Tri-Cities Basin. And this has basically been tracked by looking at detrital rocks and zircons and gravels that show that they actually came from somewhere up here. In ancestral gravels in this area, ancestral gravels down here. So, and here's the Wallowa Mountains. And so until about 3.5 million years ago, based on looking at some of the gravels actually in the big white cliffs above Hanford, the Ringgold Formation, it would appear that the that the Snake River just emptied into the ancestral Clearwater somewhere around here. And that signal in the Ringgold goes away at about 3.5 million years, more or less. Again, according to what Matthew Morris's findings are. This is orange glob is supposed to represent the Wallowas. So we have Pine Creek doing its thing and running off the Wallowas and going to the north. And then down here we have Indian Creek, the ancestral Indian Creek that ran into a huge lake called Lake Idaho that existed on much of the Snake River Plain. If you drive down to Ontario, Oregon on I-84, you'll see a lot of the sediments as you get closer and closer to Ontario. Unfortunately, I don't have any photos because I've always been too much in a hurry going down there to stop and shoot very many photos of those sediments. But at any rate, so there's this giant lake and the Snake River runs into it and runs out of it and completely bypasses this whole system. And what Matthew Morris has looked at in particular for this part of what's now the Snake River, he's looked at basically the way that rivers or tributaries drain into this river. And what he's found is that most of these tributaries drain into the river and they turn and they go to the south. And only recently have they started cutting channels that go to the north, because rivers really, really, really like to just kind of be parallel with directions that they're going. And so that is one of the many indications that he's found that, in fact, the Snake River basically was not here. This was Indian Creek, or it didn't have a name then, but at any rate, it ran to the south. But it carved a nice little canyon on its way into Lake Idaho. So this is what I'm calling the Oxbow Incident. This is my name. This is the Oxbow on the Snake River. And it's where Oxbow Dam is. The dam is here. Here's Oxbow Dam. And then they, in order to generate power, they actually bored tunnels through this neck of the Oxbow and put their generators just inside the outlet back into the Snake River. And of course, they put a little bit of water in this part of the Oxbow as well. You might also ask Jim when he talks in another couple, when he gives his next talk, about the nice flat top on the Oxbow, because I believe that the Bonneville flood overtopped this. And that's one reason that it's flat. And if you look up here, there are Bonneville flood gravels. But we're getting ahead of ourselves here. So here's Indian Creek coming down here. And right now it has kind of a confused confluence, but its confluence still goes the wrong way. Its confluence really ought to come this way because the Snake River is going this direction. All right, let's see what I've got for the next slide. Okay, so this is what it looked like before. So this is the existing Snake River channel. And what Morris has, let me go back for a minute to, Okay, so this is an odd geomorphic feature. And back in 1954, Wheeler and Cook wrote a very nice paper about the capture of river capture at the Oxbow, hypothesizing that exactly what Morris has sort of proven actually happened, that Indian Creek once ran to the south, Pine Creek, which comes into the Oxbow, I'll have another photo that shows that better, ran to the north, more or less, and actually the capture event occurred right around Oxbow, and that's right here. You can put a big X that marks the spot. And that really allowed Lake Idaho to start draining to the north. And so there's what used to was, okay, where we have Pine Creek going this way and Indian Creek going this way. So Lake Idaho, essentially, you'll notice in this map, there's this is from Matthew Morris's doctoral dissertation and the paper that he's going to publish. You'll notice that this big lake has an excursion that goes a long ways up into sort of the Hells Canyon area. And what Morris has hypothesized, and what Crook and Wheeler and Crook also hypothesized, is that this incursion actually ultimately, about 3.5 million years ago, there was a very major water level rise in Lake Idaho, probably caused by a change in the drainage system of the Snake River, an enlargement of it because of a change in volcanic the area of volcanic eruption. So this is not just Morris's idea. This is basically a pretty well documented expansion of the water level. And that expansion of water level, Morris has hypothesized and actually shown it occurred, went all the way up to the Oxbow area. Well, if you have a very ambitious stream that's cutting down this way, then and you have an incursion of water. Here's the Snake River. Snake River is running to the north, which is up here. So we have Indian Creek coming down here and Pine Creek coming down here. And Lake Idaho backing up to around here somewhere. And at that point, this little creek managed to breach this divide and capture the entire drainage of Lake Idaho. It was facilitated, this capture was facilitated by the fact that the Oxbow is also cut into what's known as the Oxbow complex, which is a shear zone that contains a lot of easily erodible myelinites and schists and rocks that, if you're an ambitious stream like Pine Creek and you're trying to acquire the drainage of a large lake to add to your little canyon cutting empire, it's pretty easy to erode your way through this. Okay, another view of the Oxbow with Pine Creek coming down here, Indian Creek running into it here, and basically the canyon cutting and capture area probably occurred not necessarily right here, but probably in this area somewhere. Okay, so that's where the capture occurred, and that was the change. So before that, we had what became the canyon as an existing kilometer-deep canyon, in which the major rivers were the Salmon River and the Clearwater River, and this is known today as basically the Salmon Clearwater River system. And this existed up until around 3.5 million years ago. And then we have a change to this becoming the Snake River system, with a whole different system of sediments coming in. Lake Idaho ultimately drains itself by about 2 million years flowing through this. So this is not like an ice age flood. This is not something that happens all of a sudden, although probably for the first 10,000 years of drainage of Lake Idaho, this would have been, you would have had major flows going through this canyon, cutting it and sizing it down. Some of the ways that Morris has dated this include not only looking at and dating the nick points on the tributary streams. So you have a level and a gradient at which streams are running quite happily, and then suddenly you begin down cutting so that these tributary streams suddenly end up cutting down more, and so there's a change in their profile. And you can date the change in their profile in a number of ways, one of which includes calculating the rate of downcutting based on what you can determine as the flow rate and what you can determine as the average downcutting rate of that river. And so what he did was he went to the portions of Hell's Canyon where there are Martin Bridge limestones, and he looked for caverns that had river sediment in them. And he used what's known as cosmogenic dating to determine the date at which these sediments were deposited in that cave and then no longer exposed to cosmic rays. You can basically do that using beryllium-10 or aluminum-26 isotopes, because what happens is as long as a rock is exposed at the surface, it's bombarded by cosmic rays. So the same would be true of a river sediment. And those cosmic rays will produce in quartz and in feldspars isotopes of beryllium. Silica will go to beryllium-10, and then you get aluminum-26 out of the aluminum. And so you have a method of determining how long this has been out of the sun and away from cosmic rays. So his date is that in Ashmead Cave, it's been about 1.2 to 0.9 million years since that river sediment was deposited. Yeah. Well, okay, so at any rate, and then what he's done is he's looked at how far above the current river level is that cave. So he's determined that 1.2, essentially a million years ago, this was underwater, and now it's not. And that gives him a date of, or a rate of incision. How fast was Hell's Canyon being cut to be able to abandon these caves? So one way he's determined, how old Hell's Canyon is to figure out how long ago these sediments were deposited, to look at the sediments here and make sure that they are from the Snake River Plain, not just from Pine Creek or Indian Creek, and use that date as a way of saying, okay, so in this case, Ashmead Cave, this is Ashmead Cave. It's currently about 1,100 feet above the current Snake River. So that basically gives him an incision rate of 1,100 feet in roughly a million years. Okay, so overall, the canyon, when the Snake River was diverted into what had been the Pine Creek Canyon, Pine Creek Canyon was already about a kilometer deep. So it was a significant little canyon, but by pouring all of the drainage of the snake through it, it basically doubled the canyon's maximum depth to about 2.2 kilometers. In the best dates that he can come up with right now are between 3.5 and 2.5 million years as the length of time that the snake has been running through here. And he's obviously would like to have better dates, but what he has is really good concrete evidence that the stream capture did occur and that the Snake River basically was diverted into Hell's Canyon through a rise in Lake Idaho at somewhere around 3 million years ago. And that rise allowed the stream capture of what had been the Indian Creek drainage to occur and divert the flow of Lake Idaho and therefore the Snake River into what had been the canyon of Pine Creek and now was going to become Hell's Canyon. So it's doubled its depth in the last plus or minus 3 million years. So it took 11 million years to carve it down a kilometer, and then 3 million years to carve the next kilometer plus. Okay, so let's take a look at the Ice Age, and this will be a quick excursion through what the Bonneville flood did, and I'm sure that Jim is going to have updates and certainly new data and a more detailed look at this. But I just want to look at this as sort of the third stage of the carving of Hell's Canyon. So as most of you know, Lake Bonneville used to be a whole lot bigger, or the Great Salt Lake used to be a whole lot bigger, and was known as Lake Bonneville. That's a little fuzzy, but at any rate, the Lake Bonneville basically overtopped its northern shoreline at Red Rock Pass, and then water poured out of this into the Snake River via pretty close to Pocatello, Idaho. Okay, so this is a more detailed map. We had one reason that we ended up with a lot of water and a sudden overtopping was, as far as I know, influx of water from the Bear River, which was melting in the mountains of Utah, put more water in here, raised the level of Lake Bonneville, and overtopped at the Red Rock Pass, which had very, kind of like the Oxbow. It just happened to pick the right spot to flood into the Snake River, because these rocks, just like the rocks at Oxbow, were pretty easy to erode. So I'm using basically data from Jim O'Connor, and he may have updates to this, but the Bonneville flood drained about 20,000, drained about half of the volume of Lake Bonneville over a span of weeks. Twice as much water as the largest Missoula flood, but spilled through a smaller opening, lasted for weeks, 18,000 years ago. The effects of the Bonneville event were mostly that it widened the canyon as opposed to deepening the canyon. And it produced a whole lot of river terraces. So if you spend any time in Hell's Canyon, you'll find a lot of nice flat river terraces that pilots of small planes just love because they can land on them, even though they're not supposed to anymore. So this is looking from a nice place called Suicide Point to the south, where there are really nice flat river terraces on both sides. Wherever there was a constriction in the flow, basically what happened was the floodwaters would slow down. They basically acted as a hydraulic dam. And so consequently, you ended up with the river pooling and dropping its sediment load, and hence you ended up with these terraces. They're particularly noticeable at Pittsburgh Landing if you ever get a chance to go there. They're really quite impressive along the area. So I couldn't get these people to back up any further for some reason. But this again is looking off the Suicide Point from a little bit different angle. One of the other consequences of the Bonneville flood, and just a consequence of having a deep canyon, is that you had a fair amount of undercutting and consequently landslides that continue to this day. And so you ended up with a lot of the rapids in Hell's Canyon. This is Granite Rapids. That make floating the Snake River a whole lot more fun and enjoyable and thrilling and dangerous than it would have been without them. So in summary, basically we have Pine Creek and Indian Creek eroding the precursor to Hell's Canyon from about 14 to 3 million years, and producing a canyon that was somewhere around 1 kilometer in depth, half a mile, 0.6 miles. Sometime between 3.5 and 2.5 million years ago, we have the capture of Lake Idaho by Pine Creek. And then that event ended up changing regional drainages and then powering the downcutting of Hell's Canyon by an additional kilometer in about, in the roughly 3 million years that the snake has been flowing through Hell's Canyon. And then the Bonneville flood basically mostly widened the canyon as opposed to deepening it, created terraces, engendered landslides that occurred probably after that flood and also to this day. And one of the big questions about Hell's Canyon, because it's such a straight canyon for the most part, is, well, does this thing follow a fault? And what Morris's work has shown is that he could find no evidence for a fault. What he saw was primarily displacement of Columbia River basalt across the canyon due to some anticlinal folding and upwarping, but no faulting. So we can't blame the canyon on a fault. It's not the canyon's fault, evidently. So that kind of wraps up what I have to say. And we can all go home now. Okay, so do you guys have any questions?
Well, I have one. The timing is really interesting to me. The Ringgold Formation, which you mentioned, the White Bluffs,
Right.
Basically that was deposited, say, 8.5 million to 3 million years ago, and then there was a real hiatus after that. So no deposition, a lot of soil development, things like that. So it was high and dry. So it was, basically, so and that was about the same time that the Snake River changed course, or created Hell's Canyon. Is that just a coincidence, or do you see that there's a connection between the Snake River, the Clearwater River, the Salmon River, and this capture of the Snake River into Hell's Canyon?
Well, I mean, it certainly would have changed the drainage systems. you know, including the probably where the Columbia was flowing in particular, and whether or not there was a, you know, an opportunity to sort of dam up the Columbia and produce the Ringgold. So yeah, but I don't know of anyone who's actually looked specifically at that dynamic. So it's a really good question, but all I can say is that the rivers change their drainages, and that would seem to be one. You seem to have a friend over there doing on something.
Yeah,
Yeah,
she's got a bone. Her
Uh-huh.
name's Coral.
Coral, okay.
Yeah.
This is Pepper. So yeah, I mean, I don't have any answers to that. I think it's a great observation and a really good question. I suspect that I know that there are a couple of papers on the Clearwater salmon drainages and where the river actually went. But it would seem as though, yeah, right at about 3 million years, there was this change in sedimentation. So.
Yeah. I'd seen some references to the Snake River actually flowing north and capturing into the Salmon River, maybe on the eastern side of Idaho. So I don't know, it's like it's flowing backwards. I don't know much about that, but anyway, well, thank you very much. It was a good lecture.
Yeah, I think, you know, ancient river systems they're really intriguing because you only get these little tiny glimpses of them. It's kind of like the Eocene channels that were coming, you know, from Idaho across Eastern Oregon. You get the gravels in particular are usually between the basalts and the granitic rocks. I don't know of any between the basalts and the pre-tertiary greenstones. And so, you know, you don't have a chance to look at this very often enough to actually begin to get a feeling for where those channels went. You know, I know that when I was mapping in the Greenhorns, back when there were still, I think T-Rex was still wandering around then. Certainly the mammoths. There was, I encountered a couple of those in the channels with little fragments of palm trees in them. But that was way over, you know, that was another 90 or 100 miles from the Wallowas in the Greenhorns and the Strawberries. So they were obviously extensive channels, but exactly where they came from and exactly where they went to is still a puzzle. Yeah. Okay. Well, thank you very much for the opportunity to confuse everybody.
Thank you so much. We really appreciate it. I feel like I definitely learned a lot about things that I had never known about. So that's good.
Okay, super.
Yeah, it broke down my simple assumption. Thank you very much.
All right, you're very welcome, guys. You have a good evening, and I'll sign off to you and also to all of the furry friends that seem to be cropping up everywhere.
Thank you, Alan.
Take care. All right, bye-bye.
Bye
Bye-bye.
now.
Hey.